In the name of God, the compassionate, the merciful, Engineering Plasticity course, Chapter 1, Introduction, Part 1. Now, in this introduction, what we are going to do is to ask you some questions, right? Ask some questions and try to answer these questions. Now, I present all of these questions here right now, but the answers to these questions will be given gradually. So you must be careful to notice the answer to these questions as we go by. And if you feel that any of these questions have not been answered, then you can ask me again in the session that we have online on Tuesdays. The first question is, what is the physical nature of plastic behavior of materials? Right? Plastic behavior, we want to know what is its nature, what mechanism it has, how does it work? How is the plastic behavior of a single crystal? Then we want to consider a single crystalline metal and see how it is deformed plastically. How is the plastic behavior of a polycrystal? After considering a single crystal and understanding the plastic behavior of a single crystal material, then we go forward and move to polycrystalline metals. Polycrystalline metals are in fact the real materials that you see every day, and we use it in many products. How is the plastic behavior of a polycrystal? So we want to know how does plastic deformation occurs in a polycrystalline metal. That's the question. Is there an equation defining the plasticity of metals? You see, when we put pressure on a metal, or when a metal is under tension, if the force increases enough and we pass the yield point, then we go into the plastic region, and the curve defining the plasticity could be defined by an equation. So here, that's the question we have asked. Is there an equation defining the plasticity of metals? How does the Bashinger effect the plastic behavior of metals? Bashinger effect is an effect that happens when we deform the metals plastically. We want to know what effect, what influence it has on the plastic behavior of metals. How does the anisotropy affect the plastic behavior of metals? I'm sure that you have come across this Bashinger effect and anisotropy effect, but here we want to know how do they influence the plastic behavior of metals? Which theoretical models are best to predict the material's behavior? Okay, here again, in the previous question we asked, is there an equation defining the plasticity of metals? Here we would like to know whether we can define a theoretical model to predict the material behavior. We could use these models in our simulations. What could one get out of the tensile test? Tensile test is a very famous test which we carry out on many metals to characterize them. And here the question is, what do we really get out of this test? What kinds of plastic deformation are there? This is interesting also. how many plastic deformations? What does it mean? How many? Or what kinds? We will deal with this question later. What is the influence of temperature on the material plasticity? So the plastic deformation in the room temperature, or in very high temperatures, or in very cold temperatures. What are the differences? What are the effects of strain rates on the material behavior? Strain rate, in fact, is to do with the velocity of loading. For instance, static loading, dynamic loading, how fast we are loading. That the faster we load a specimen, we say the strain rate is higher. So we want to know what effect these strain rates have on the material behavior, especially obviously in the plastic region. As you can see, we have this question again presented here. What is the physical nature of the plastic behavior of materials? So as we go by in every slide, we present these questions and try to answer them. Now, the tensile test, the famous tensile test. In fact, the most famous test in the mechanical engineering, or maybe in engineering as a whole. This is the most famous test. What is it? Well, we have a standard for the specimens for this test. The standard is a dog bone shaped specimen like this. Okay, this is a ASTM standard specimen. As you can see, this place which we call gauge length is about 2-inch length, which is about 50 millimeter length, and 2¼ of an inch is here to there, and the diameter is about 1/2 of an inch, and the diameter of the ends, which the grippers will grip these ends, is about 3/4 of an inch, and we have a fillet here, a fillet radius of 3/8 of an inch. Okay, so we put the specimens in these grippers, these jaws, and these are this is some kind of schematic sketch. So we have a press, hydraulic press usually. These are the plate ends of the press, and we grip both ends of the specimen by these grippers or jaws, and we have a load cell here and extensometer in here. So what happens here is that as the crosshead moves down, sometimes the upper crosshead moves up and the bottom crosshead is stationary. Doesn't make any difference. So as you can see, as the crosshead moves downwards here in this sketch, the specimen is extended, okay, because it's fixed between this jaw and this jaw. So this is a stationary. As this moves down, the specimen extends. This extensometer measures the extension, how much the specimen length is extended. So this measures the change in length. Also, we have a load cell here which measures the load. As we move down, the load increases, and the load cell measures the load. So what we measure in the tensile test is load and extension, increase in length and increase in load. These are what we really measure. Okay then. So from those measurements we can derive values for stress and strain as shown in here. Okay, stress obviously is load over area, and a strain is the change in length. Okay, so this is the natural strain, as we call it. We have also engineering strain, which is delta L over L0, or L minus L0 divided by L0. That is engineering strain. But this is true strain, or natural strain, as we call it, and it's shown by ln over L over L0, and this E in fact is L minus L0 divided by L0. So this is engineering strain, this is natural strain. We can easily derive these relations. Now then, what we have here is the behavior of the material. This shows the behavior of the material. As you can see, this is the specimen, as we showed in the previous slide. The specimen at the beginning of the test looked like this. As we go along, in fact, we increase the distance between the platens. The lower crosshead in the previous slide moves down, the length is extended, and the load is increased. Okay, this is the extension in length, and this is the increase in load. But we have shown this by stress and strain. Now, we reach a point here. As you can see, this is increased in length. We reach a point here, and then at some points we see that a neck is formed, and this neck is unstable, and it suddenly changes to this, and it becomes very narrow and suddenly breaks off here. Okay, so if we look at this behavior, we will see that we have a straight line here which shows the elastic behavior. In other words, for a certain amount of stress, we have a certain amount of strain. Stress and strain are proportional to each other up to some point, which we call this point the proportional limit. After the proportional limit, we see that the behavior of the material is no longer linear, because here is linear. Sigma is equal to E epsilon. That's how we show the behavior in here. So after this point, after the proportional limit, we say that the material yields. And we see the plastic behavior. Here is the plastic behavior. We have this point here, tensile strength or ultimate tensile strength, this point M. As you see, is a maximum point on this curve, and after that, suddenly the stress drops. Okay, the value is decreased, and this is the fracture point. Okay, so if we look at this shape, the behavior of the material can be understood by this simple curve. Okay, very simple curve, very simple. In fact, we say that this is simple tensile test because we have only load at one direction and changes in length at one direction, and of course we have changes in width also. I mean, the other dimensions of this specimen changes as well. But in fact, we are moving in one direction. That's what I meant. So if you look at this curve, we realize a lot of things. We can understand the behavior of the material. It's very strange that with a very simple test, we could get a lot of information about the behavior of the material. But we shouldn't be fooled by this, because many of the behaviors that are related to the microstructural changes of the material could not be developed here, could not be taken out of these results. Okay, so we shouldn't be fooled by these results. We call these results phenomenological. That is from the macrostructure of the material, not from the microstructure. We don't know what's going on in the microstructure with this test. With this test, we could get this point, which is proportional limit, this point, which is the yield point, this point, which is the UTS, or the ultimate tensile strength, this point, which is fracture. The area under this curve, of course, is sigma times epsilon, and that is F times L divided by the volume. So F times L is the work or energy. So under the curve, the area under the curve is the energy. For instance, if we get it up to here, if we drop a line in here, then this area is the energy absorbed by the material up to this point. The energy absorbed up to this point is the energy needed for the fracture. We call this energy under the curve toughness of the material. Also, this axis shows the percentage of elongation, and it is a measure of ductility of the material, and this point shows the strength of the material. This shows the yield strength of the material. Okay, so we can get a lot of information out of this curve.